Okay. Hello, everyone. Can you hear me? Hello. If someone can type in the chat, if you can hear me, that way I'll know if you can hear me. Oh. Okay, good. So Guha can hear me. And can you hear me? Can you hear me well? Or am I like, okay. Okay, great, good. Okay, so hello, everyone. Some of you may have joined us from last week, and some of you may be first time here. So let me just explain what I'd like to do here. So the idea is, you're stuck at home, the whole is stuck at home. It was suggested to me actually by my friend, the CEO of Starkware, Uri, that it might be good to sort of share information about some intuition behind the math of proof systems in general. So I'm following on this. And last week we spoke about fast Fourier transforms and how they're related. So they come from signal processing, but somehow they show up in Starks and Snarks and other kinds of proof systems, and it's very strange why they do so. And today I want to answer a different kind of question that is also very strange and is also different and separate from the stuff that we talked in the past. So in order to do this, I'm gonna jump over as usual to using the whiteboard. So let me just check whether I'm gonna just initially gonna ask and see. So the question for today is, why polynomials? Polynomials. Something is very strange here. It's going very slow. Why polynomials? Why do they show up? Why do they show up in ZKPs? That's the question we would like to answer. So I'm just jumping back. Let me just ask, can you see the screen? The whiteboard, just want to make sure. Okay, cool, good. So I'll stop asking, and from time to time, I'm going to go back and sort of ask you if you can, hear me well and see me well and things like that. So basically, that's what we're going to do. So. And this time I even prepared a little bit of stuff beforehand. So looky here. First of all, what do we mean by polynomials? So here you can see a degree 1 polynomial. So this line here is a degree 1 polynomial, right? You may remember it from grad school or maybe even before. So this line y equals ax plus b. And here below, we see a quadratic polynomial, parabola, y equals x squared plus bx plus c. And more generally, when we say polynomials, we mean some expression of the following form, p of x. So we'll usually define the variable in the polynomial by x. And p of x is this expression, summation. I goes from 0 to d of ai, that's a coefficient, times x to the I. So x is this variable, and the largest non-zero coefficient is known as the degree of the polynomial. So just to give an example, wait a second. So like here you can see that this is a degree 2 polynomial, and here this is a degree 1 polynomial, right? Because this is x to the 1. Good. But in general, we could have larger degree polynomials, and the degree is the very important parameter. Good. So these are polynomials. We know them from at least high school, right? They have a lot of nice properties. But what the hell do they have to do? What role or what connection do they have to these kinds of statements? So why are they used in these things that we call succinct, zero knowledge proofs of computational integrity, right? Why do we need them there? So for instance, here's an example. Here's a statement that actually, our system is going to be proving soon. And it's just one example of many kind of computational integrity statements. So we have a state of an account system, a whole bunch of accounts, and we have a Merkle root for the state of the account. So down here in the leaves, we have many, many, many accounts, Alice, Bob, each one of them have their funds. And basically, we would like to move to a new state of the system. And we would like to submit to the chain some proof that we can transition from state A to state B. And all that the main blockchain knows is about the Merkle root of the state of the system. And basically, we would like to assert that based on seeing 10,000 valid transactions and processing them, there is a new state of the accounts, which leads to a new Merkle root. And we would like to move the system from A to B, and we want to prove this thing. So this is a computation that talks about financial transactions and checking all kinds of sums and checking maybe signatures or all kinds of cryptographic things, but it certainly does not have anything to do with polynomials. So why is it, and you'll have to trust me on this one, but why is it that all the proof systems that are deployed or considered to be deployed today in various blockchains and elsewhere in the world, why do all of them go through polynomials evaluated over finite fields? It's really, if you think about it, somewhat mysterious and uncalled for. Why do we need this connection to happen? Right, this weird thing happens all the time. Let's refresh this. Sorry. Sorry about that. That's part of the problem with these systems. So the main question we would like to answer is, what is it about polynomials, or what properties of polynomials make them so useful for appearing in all proof systems? And again, I want to stress this point. All of the proof systems that you heard about recently, right, with all the marvelous things, so I'll just mention a few of them. Of course, Snarks and Roth 16 and Pinocchio and bulletproofs and Plonk and Slonk and Aurora, Ligero, Starks, Marlin, Fractal, Halo. All of them involve polynomials somewhere or another, right? All of them. Why? Why are they needed? So there are certain properties that are going to be really, really useful. And the purpose of this informal talk is to give you some intuition into these, these properties. So I just want to pause here and just ask, once again, are you following? Like, in terms of the sound, everything okay? All okay? Just to make sure that I'm not speaking, because I have no feedback here. I'm actually watching the other screen. So just if you can let me know if things are, if you can see the screen. Okay, good. Okay, great. So I'm jumping back to starting to answer this question. So, and now I want to sort of revisit something that I explained last time, but I want to go over it, kind of slowly. And I want to say that there's this really good, proof system that you can think of it as the mother of all proof systems, and it already involves polynomials. And the main focus of today's talk is to explain why it involves polynomials, what properties of polynomials make them so useful in this thing. So this is a description of a proof system that is too good to be true. you don't actually use this exact proof system, but it is sort of the mother of almost all proof systems out there. So the proof system, as always, starts with some statement of computational integrity. Just 1 second, sorry. Okay, so we start with some statement of computational integrity. For instance, the prover, and that's stage 0. The prover comes and says, well, I want to assert that it's okay to move the system from state A to state B based on processing 10,000 transactions. So this is a very computational statement. Now, in this ideal proof system, the verifier actually responds with a bunch of degree bounds, a small number of them, like 3 or 4 or 5 of them. And it says, you know what, if you want to prove this statement to me, here are a bunch of degree bounds. You know, this one could be 1,000, this could be 1,000,000. Basically saying, you know what, give me some polynomials of these degrees. And that's what I need in order to verify. And then, the next step in this process is that the prover somehow supplies the verifier with a bunch of polynomials. The verifier has asked for k polynomials. Think of this number as 2 or 3 polynomials. And the prover somehow supplies the verifiers with these 2 or 3 polynomials. Their degree is going to be bounded by the degree bounds that the verifier has asked for. Okay? And the next stage is one in which basically the verifier does a single step of sampling, and it samples a single element from a domain between 0 and p minus 1. And usually this p is some large number, like p could be smaller than I don't know, 2 to the power 256. So it's a pretty large domain that the verifier samples from, but it's really just one sample that the verifier makes. And again, this is a generic proof system that you can use in order to prove and verify any statement out there. Now the next step in this process is that the prover basically answers with the value that these k polynomials take point z. So the verifier has sampled a random point, and the prover answers with these values, the point z. And then based on this information, the verifier sits and examines the answers and decides whether to accept the statement. So this was the original statement. The verifier decides whether to accept that statement or to reject it. So the main theorem that I want to tell you about this thing, and it's not too hard to prove, but I just want to share it with you, is the theorem below. The protocol, this process that we just described here that has these steps, has only one-sided error, meaning that if you have an honest prover, if this statement, just 1 second, sorry about this. Okay. If this statement is correct and the prover operates honestly and actually supplies the correct polynomials of degree di, then whenever the prover gives the God-honest answers of these polynomials for any point z, the verifier will accept and answer yes in this case. That's the good case. And in the bad case, we know, and that's the more important part, that if this statement is false, suppose it's not legitimate to move from state A to state B, so the prover is actually trying to cheat, then no matter what polynomials of these bounded degrees the prover gives, the probability of error, meaning the probability that the verifier decides yes, even though the answer should be no, that's the probability of error. This probability of error is at most the degree divided by this p. So if this p is 2 to the 256, and typically the degree is, the degree is typically something around, like, I don't know, let's say 2 to the 30 or less than that. I mean, it's less than that. So in this particular case, the probability of error would be smaller than 2 to the minus 200, which is a very, very small probability. So this is an ideal proof system that has perfect completeness. It never makes an error when the prover is honest, and its probability of error is smaller than the degree divided by the domain from which you sample your z. So this is already some answer, a first order answer to the question that we started with, right? We said, why is it that polynomials are useful for answering, questions about computational integrity? The short answer to that is that there is this magical proof system that is really the mother of all proof systems that we have deployed so far, that the world has deployed so far, in which as long as you follow this protocol in which there are given, you specify degree bounds, the prover gives access to polynomials, there is even a single sample and a bunch of answers, you can basically decide any question. And I want to just emphasize a few nice properties of this protocol that are really good. So the number of queries, for some reason, this is working very fast, is k. It's very small. And it's much, much smaller than d, which is the degree. So typically, this k is going to be less than 10, or in the examples, we'll see it's going to be like 2 or 3, whereas the degree could be really large, 1 million or more. And essentially, the number of queries and the amount of information that is passed between the prover and verifier, right? The verifier is sending a single z, and the prover is essentially sending, just k field elements. So that's all the information that is transferred. It is much, much smaller than the degree. So we already see that there is very succinct communication complexity. A tiny amount of information is passing between the parties. The other thing I want to say is that this is a transparent system, meaning there's no setup required and there's no trusted setup required. The only place where randomness is used is when the verifier selects z, and this z there's nothing magical about it. It just has to be randomly sampled from the set of all possible options. Okay, so that's another thing. I just want to mention it's also post-quantum secure for reasons that I don't want to go into. And yeah, so it's a really cool and good proof system. But this doesn't explain why. I mean, what is it about polynomials? I mean, for instance, we could ask, why polynomials? Why not have the prover give access to some other thing like a computer program, or I don't know what, a matrix, or maybe some other mathematical object? What is it about polynomials that allows us to do this thing? And it's not all mathematical objects that have this property, right? If it's some other weird surface or object or matrix or something, you don't get this kind of protocol. It just doesn't work. So there are some special properties of polynomials that enable this kind of succinct, high soundness, highly efficient protocol that's also transparent and post-quantum secure. And that's what I want to explain in this talk, in the remainder of this talk. So let me go back and pause for a second and just ask, are there any questions so far? And I already see that someone has asked a question, so you can go down to the bottom of your screen and ask a question. So the first question is, why can't the verifier perform the calculation of PIZ herself? She gets the polynomials. That's an excellent question. So in this model, which is it's an abstract ideal setting model, actually the verifier doesn't need to receive all the polynomials. She just needs to know that the polynomials are first given, then z is sampled, and then the prover must answer according to the polynomials that she sort of committed to or has already written down. If all these polynomials are indeed transmitted over to the verifier can answer these questions herself, but then we lose all succinctness because these polynomials contain as much information as all of the computation. So in the case of a statement talking about 10,000 transactions, the polynomials will contain more information than all of the information about those 10,000 transactions. So we don't want to have the prover send all of the polynomials over to the verifier. That's why. So that's why I'm calling it the too good to be true, because we're in this model where we assume that the prover has committed to certain polynomials, and the polynomials are of low degree, and then the prover must answer according to some random query. Okay, are there any other questions so far? Okay. So let's go back to that slide. And now I want to say, so I want to put down sort of a list of good properties of polynomials, and then we'll sort of fill in the list. And I'm pretty sure that we won't be able to put in all the good things about polynomials and mention them. So, but nevertheless. So I want to start putting all kinds of good things about polynomials. So polynomials, and the first thing I want to talk about is that they are excellent error correcting codes. They have a magical way of giving us redundancy, and this redundancy is what is going to allow us to conduct the analog of polling, right? So, if we want to estimate with a high probability who will win the election. So we don't need to go, the winner of the election is going to be based on asking, the votes of all citizens. But nevertheless, in all countries, we sort of, before that, someone conducts a poll. And this poll samples a very tiny fraction of the population and estimates the answer based on that poll. Now, it's not always a perfect system, but the mathematical basis of polling basically talks or says or proves that even if you take a very tiny sample that is exponentially smaller than the size of the population you want to base the result on, you will get with high probability a very good answer. Now, we want to have the same kind of phenomena with respect to computation. We would like to take a very small sample. If you remember the protocol we just described, we're going to sample just one field element. So we're just going to ask for the value of polynomials at a single point, and yet we would like that point to be sort of an excellent, polling sample size. So for that, we need to add a whole lot of redundancy, and that's the first property of polynomials that we're going to use. So this is the first thing that I want to explain. I want to tell you how you can use polynomials to get error correcting codes. And let's start with an example. So suppose I want to add redundancy, or I want to keep information in a way that is very redundant. So I want to take a message. So here is going to be the sort of the message domain, which means in this case, I want the message that has 4 symbols. So my message has 4 integers. Maybe it's going to be an encoding of some word in some language or something. And then I want to transmit it or save it on some, on some medium that has a lot of noise in it, and will sort of information will be, maybe messed up. And I still want to be able to recover the original data after the fact. So for instance, let's suppose that my message basically consists of 4 zeros. So basically what I do is I plot these 4 zeros at these 4 points according to some sequence. And then what I do is I interpolate. I find the polynomial of minimal degree that must pass through these points. And it turns out, so you probably remember, right? Through every 2 points, there passes a unique line, which is a degree 1 polynomial. And through every 3 points, there passes a unique polynomial of degree at most 2, and that's a parabola, right? And you can extrapolate from this that from every 4 points, there must pass a unique polynomial that is of degree less than 4, meaning 3 or below. Now, in this particular case, actually, the unique polynomial of degree less than 4 that passes through these 4 points is a very simple polynomial. It is actually the sort of, it's the line. It's the 0 line. Now what we do in order to encode the message that is the 4-0 symbol is we take the interpolating polynomial, in this case it's 0, and we evaluate it at a bunch of predefined points that I'm going to call D. So this is the evaluation domain. And okay, so if our message was 4 zeros, we get this polynomial, which is a whole bunch of zeros. It's encoding. This is the stuff that we save. We save a long sequence of zeros. Now, suppose we have actually a different message. So suppose the message that we have now is somewhat different. It has 3 zeros here, but here it's actually something non-zero, like a 1. So we do the same process again. We find the polynomial of degree less than 4 that passes through these 4 points, and we evaluate it here. And I don't know exactly what this polynomial looks like. I'm just going to imagine, you know, maybe it goes like this. I don't know, something like that. And then, it, I don't know, just wiggles around. So the encoding for this other message is going to be these points. So we take these values, and that's what we save, right? We like the y values. So maybe, you know, the sequence is going to be the numbers. I don't know what, I'm just imagining. 3, 2, 2, then it goes up again, 3, 1.5, blah, blah, blah. For this guy, we know that the encoding was a whole bunch of zeros. And the main property of error-correcting codes that we also see here is that even if we changed a single bit in the message space, the encoding has become very, very different. So there's going to be no 0 in the encoding of this thing. And why is this the case? Well, we took a polynomial of degree 3 that happens to have already 3 zeros at these 3 points. A polynomial of degree 3 cannot have more than 3 zeros. So it will have no zeros here. It must be non-zero everywhere. Whereas the polynomial, the red line, is all zeros. So notice that the distance, the number of entries that are different between this guy and this guy is immense. It's really, really large. And it's not a fluke. It doesn't happen just for these two messages. What we have is the following theorem, which is actually not too hard to prove. For any two messages, m not equal to m prime of size d, meaning they have these symbols, their encoding must differ at the size of the evaluation domain minus the degree many points. In other words, we say that this error-correcting code that uses polynomials to encode stuff has very good distance properties. You cannot find two messages that will have an encoding that looks very similar. And again, why is this important? So again, we're going back to asking about this property. Why is this property important? Why do we need an error-correcting code if we want to construct a succinct proof system in general? So this has to do with this property. We would like to do this polling, right? We would like to sample a single element. So one sample. And we would like this sample to say something about a very large degree polynomial, or a very large message that contains a lot of information. And in order for that to be the case, we need a good error correcting code, so that, I mean, even if there's something that is off just by one bit, like, our computation, there's just if we look at no statement, maybe 9,999 transactions are perfectly okay. And just one transaction, you know, there are a bunch of zeros at the end. That's the transaction that I'm paying myself some money. You know, just a number of zeros at the very end of it. That's sort of the message that we would like to argue is everything's okay about it. We would like this tiny change in the information to sort of be spread out over a huge area and be easily discernible and easily found. And for that, we need good error correcting codes. So summarizing this, the very first property that we use of a polynomial is that they are excellent error correcting codes. And what this gives us is that this leads to good sampling polling, which then leads to being able to do things succinctly. So proofs are all about succinctness, and the error correcting code property and the redundancy allows us to get the succinctness. So now I want to pause for a little bit and ask, are there questions about this part? So I see here a question that says, does V verify via some sort of cut and choose the evaluations of PZI? Not really. It's more like the verifier basically just asks for a single evaluation of these polynomials at a single point. That's it. I hope that answers the question. Are there any other questions so far? Okay, so I'm going to ask if you can, someone in the chat room, am I going too slow, too fast? You know, should I go faster? Should I go slower? Just type in the chat room whatever you feel. And meanwhile, okay, so please in the chat room just say if you want me to go slower or faster, you know, in terms of the math proficiency. Okay, so I just want to answer more questions. For me, error correcting code is a mechanism to correct the sequence of data. Here it's rather to check that the sequence is correct. That's an excellent question, Robert. So what happened with error correcting codes, right? Originally in the 40s and in the world of information theory and error correcting codes, they were originally thought of as a mechanism to preserve data, right? With no semantics and nothing about the semantics of the data that is there. Basically, you just want to make sure that the files are maintained correctly or are transmitted correctly. But it turns out that certain error correcting codes come with extra properties, which will be the topic of the next item. And these extra properties allow you to beef up the error correction and have it talk not just about whether the data is preserved correctly, but whether there are semantic computational integrity properties reflected in that data. And that's really the magic of proof systems using error correcting codes that were started, this topic was discovered in the mid-'80s and has been a theme since then. So in the 40s, it was about using error correcting codes for maintaining the correctness of data. And then starting in the 80s up till now, certain error correcting codes are used to sort of also prove the semantic properties, the correct computation properties. Okay. Okay, so I think it's either same pace or a little bit faster. Oh, wait, is there a reason you choose the all-zero polynomial? Yeah, there's a very good reason. Whenever I need to think in my head about some, generic polynomial, I always go with the zero polynomial. And the reason is that it's very easy for me to describe a lot of properties of the zero polynomial. For instance, I can easily evaluate it anywhere. So I really like the zero polynomial. Whenever I need to pick one, I work with it. There are other reasons, like, in a linear space, the zero vector has a very special place, and the zero polynomial corresponds to that. It's sort of the origin of the linear space of all polynomials. So there are other reasons, but for me, it's just, that it's easy for me to think about it. Okay. Any chance to do any of these proofs deterministically with polynomials? Of course, with spending more time. Yeah, you could do everything deterministically, but if you allow no randomness, then you immediately lose all succinctness. So you won't save anything in the running time for the verifier, and you also lose the zero knowledge. So randomness is unfortunately necessary for both privacy and for scalability. And I don't know of any other uses for proofs other than either scalability or privacy. So if you don't allow randomness, you're going to lose all of the good properties of the proof systems. So I guess, yeah, you can do it deterministically with polynomials, but then you lose all the properties that you want the polynomials for. Let me see if there are other questions. Does Zcash put the ZKP in the discrete log field to make it non-interactive, which makes it not post-quantum safe? So that's a very advanced question that I prefer not to answer, not because it's not a good one, but just it would take me too far away from the main topic of this lecture, which is much simpler. Okay, yeah. So you don't making it non-interactive in discrete log field. I prefer not to answer it. You can send me an email online and I'll answer that. What about polynomials is not good for proof systems? Well, you could always hope for things that are even more efficient. I mean, polynomials, encoding them and takes quasi-linear time. There are error correcting codes that you can encode and decode in strictly linear time and very fast, all kinds of like turbo codes and other stuff. So like if you want to use, there are faster error correcting codes out there. And there are other bad things about polynomials, but they're pretty darn good. Okay, so I will now go on to the next topic, and I'll go just slightly faster. So the next thing I want to say is that polynomials, so this is property number 2 that's really, really good. So property number 2 is that polynomials have efficient, something is acting up in the speed of this, the way the whiteboard interacts, but never mind. Have efficient batch zero testing. And again, that helps us with succinctness. So I want to explain now what I mean by batch zero testing. And for that, remember we had this generic protocol where the prover wants to prove a very generic statement. But now I want to take a special case example of it and just discuss that and use it for zero testing, okay? So let's say that the statement that the prover wants to prove is something a little bit simpler, okay? So the statement is what's written here. Suppose the prover wants to make a statement that, bear with me here. We're going to make a point with it. But the prover wants to say, you know what, there's this polynomial that is a very large degree. So like, think of D2 equaling a million. Okay, so it's a very large degree, well, even 10 million. So it's a huge degree polynomial. And there's a statement that says, you know what, I want to prove to you that this polynomial that is of degree 10 million has the property that if you evaluate it on, the points 1, 2, 3, up to a million, you will always see a 0. So it does not mean that the polynomial is 0, because its degree is much larger than that. Its degree is 10 times larger than a million. But this weird statement says that the for a million points, the prover, this polynomial evaluates to 0. Okay. Now, it's a strange statement, but suppose we would like to verify its correctness succinctly. So how do we go about doing this? Well, we have access to this polynomial, P2. And we can actually ask for other polynomials maybe to help us in this process. But we want to make only a single query. So, and we want the theorem that we specified previously, we would like it to hold. Let me just remind you what the theorem says. The theorem says that the honest prover always succeeds, but the probability of error, if the prover is cheating, is at most, the degree divided by the size of the domain that you evaluate from. So let's look at this statement again, and let's look at some things that won't work. So one thing that won't work is going to be just sample, right? Or, one thing that's not going to work is to go over all entries, because we're only allowed a single query. So that's one thing that won't work. Another thing that won't work is to sample some point, because what if the prover is cheating by just picking one of these points and having the polynomial not be 0? Our odds of finding that are 1 in a million. And we want the probability of error to be extremely small, whereas here it's going to be extremely high. So we can't do that. We need something else. And that's our next topic, batch verification of zero testing. So I'm just going to use this space. So what do we mean by that? We have this set S. In our case, it's the set of points 1, 2, up to a million. Set of a million points. I want to define a polynomial that is the unique polynomial that vanishes on these million points. So I'm going to define it as the vanishing polynomial of the set S. It's a univariate polynomial in X. And basically, I just, go ahead and make sure that this polynomial vanishes on all points. So I just write I goes from 1 to a million. So let's see. For any one of these points, if we plug it into this polynomial, the polynomial will vanish, right? The number 7. So one of the terms is x minus 7. If you plug 7 into it, you get a 0, and the whole polynomial vanishes. So notice that the degree of this polynomial Vs equals exactly the size of S. So this is the unique polynomial that defines S in the sense that it vanishes exactly on these points with multiplicity 1. Okay, so why is this good? Here's a fact that is not too hard to prove. And the fact says that a polynomial P of X vanishes on the set S, on any set S, if and only if there exists some other polynomial, let's call it P tilde of X, such that two things happen. First of all, you can write P of X as P tilde of X times the unique vanishing polynomial of X. And the second thing is about degrees. The degree of P tilde is exactly what you think it should be, equals exactly the degree of P minus the size of S. So I'm not going to prove this fact. It's not too hard to prove, but you're just going to have to trust me on this. So now, if we have this fact that there's a unique way to structure a polynomial in case it vanishes on a specific set of points that we know in advance, now we can go back to our challenge and basically solve it. So let's go back to this protocol that we wanted to solve, right? We wanted to know whether we want to solve this statement, right? We want to know whether P of Z, P2 of Z vanishes on all of these points. And we want to do it by using a single element. What we're going to do is we're going to ask, as the verifier, we're going to ask for, D1 which is supposed to be the degree of P2. Sorry, let's call it, D2. That's the degree of D2. And we're also going to ask for D3, that is going to be equal D2 minus 1,000,000. And now the honest prover should give us, basically send us P2 and also send us P3 that is supposed to be what we called P tilde 2, such that it's supposed to be the case P2 of x indeed equals P3 of x times the vanishing polynomial on x. So now, but the only thing we get, okay, so this is what the prover should send us in stage 2, right? This is what the prover sends us. Now, in stage 3, we go back and sample a single z. And now we just ask for, P2 of z, and we get P3 of z. And here's how we decide. So we decide yes, if and only if the answer that we get, P2 of z, indeed equals P3 of z times Vs of z. So let's see what happened here. We made just one query. We just asked for z, and we just got 2 answers, which are supposedly, these are the values of P2 of z and P3 of z. And then we did a simple computation, which involved, getting one of the answers and comparing it to the second answer times something that we can compute ourselves, because we know what S is and we know the formula for Vs. And then if we see an equality, we accept it, and otherwise we reject. So why does this work? Well, if the prover was honest and P2 does indeed vanish on all these points, then everything works fine, and for every z, we accept. Whereas if the prover has cheated, so we actually have an inequality here. So here we have an inequality. And then this is a polynomial of degree d, and this is another polynomial of degree d, but they're not the same polynomial. So they must be different on at least the size of the evaluation domain minus the degree many points. So the probability of error, the chance of making an error, let me just write this here, the probability of error equals the probability that P of z, well, P2 of z equals P3 of z times Vs of z. And all of this is conditioned on P2 not equaling P3 times Vs. And this whole probability is at most the degree, but we sampled, this is the probability over z, but we sampled from a very large field, so the probability of error is very, very small, and we said this is like, something like degree over, let's say we took a field with 256 bits. So it's something really, really, really tiny. Okay? So summarizing this part, zero batching, we have efficient batch zero testing. This allows us so this facilitates taking a single sample, checking many many facts. Each one of these facts is whether the polynomial vanishes at a point. Okay, so now I'm going to pause once again and ask, let's see if there are questions. I'm going to answer the questions. So the first question is, what about polynomials? Okay, it's not good for proof systems. We already answered that. Next question is, that I see here. Is there any chance to do any of these proofs deterministic? Oh, we answered this as well. Is there any answer? We answered this already. Is there any chance doing these proofs deterministically with polynomials? So we already answered that. Let me go to the does Zcash. We answered that. What kind of statements can be proved? For example, proving knowledge of a hash, pre-image, or set membership. The answer to that question is that you can prove any statement for which you can write a program that computes it. We cannot see the whiteboard. Can you see? Well, okay, I saw this only now. You know what? Next time I go to the whiteboard, I'll go back and ask whether you see it. Okay. Let's see what other questions we have here before going back. Can we prove that P2 of Z vanishes in some points, say on only the x points from S, without revealing on which points exactly? The answer to that is yes. We can, if you want the statement to be that there are certain points inside S, x many points, on which the only on them you vanish, and you don't want to say which points they are, yes, you can prove this as well. But that's an exercise. Yeah. Okay, so let me ask again, how was the speed? Was it fast or slow? Should I go faster? There's one more topic that I want to cover in this. It's not all the properties, but there's one more thing that I want to cover. So should I go faster or slower? Just don't forget the board a bit faster. Okay. Faster is okay. Okay, so I see there's sentiment to go faster. Okay. Let's increase the speed a little bit. Okay, can you see? I hope you can see the board now, right? We'll go a little bit faster. I see Petra is asking not much faster. So we'll go just a wee bit faster. So good. So the last point I want to talk about is this thing that is called so they have what we call the multiplication property. By the way, I want to apologize for some reason that I don't understand why my pen on this pad this time is working like is responding very, very slowly, and I don't quite know why. So it's causing like my handwriting, which is always pretty bad, to look even much worse. So in this case, what we're going to do is take yet again the statement that we started with and change it just one more time. And that will be the last thing that we do here, even though you can do a lot more. Good. So let me now use the eraser property, actually. Just erase this thing, right? It's not needed here. Good. Okay. So suppose now that the statement we want to prove, and this already feels a little bit like something that you might need when proving computational integrity. So the statement is that it's a kind of a type checking statement. Basically, the statement says, you know what, polynomial number 1 has the property that on the first million points, if you evaluate it, it won't be all 0, but it would be, I assure you that it takes on only a Boolean type. So it's only 0 or 1. And this already feels much more realistic, right? Because maybe if I want to prove to you that my computation has, correctly processed all of those 10,000 transactions, maybe, when you compile it into assembly or whatnot, there'll be all of those, flags, Boolean flags lying around. And part of what you want to do is check that they have the right type, which is a Boolean type. So it's a simple, constraint to talk about, type checking constraint, but it is already, you can see that it has some computational feel to it. It's not so much algebraic, right? It talks about something very computational. So we want to prove this statement. Again, remember, we're only allowed a single, query, and we want the probability of error to be very, very, very small. Okay, so that's our challenge, right? Because of course we can read it by reading these million queries. And again, we think of, let's say that the degree of P1 is, all we know about it is that it's at most 10 to the 7. So 10 million. It's a huge number. We don't want to read all of it. So let's deal with this thing. What are we going to do? So first of all, I want to talk about a constraint. So I want to define a polynomial that vanishes on exactly 2 points, on 0 and 1. And I want to think of it as a constraint that I want to check. So here's a constraint. Let's call it the 0-1 constraint. It's a Booleanity constraint. It takes a certain value, and it has exactly 2 things that make it vanish. Right, we can even open this one up. So it's x squared minus x. So this is a constraint that is satisfied, meaning it vanishes on only 2 points, on 0 and 1. In general, when we work with polynomials in algebra, it's very good to associate true with 0 and false with everything that is non-zero. So that's what we're doing here. To satisfy this constraint, there are exactly 2 ways to do that. Either you plug in 0 or 1. So now let's see what happens to if we take C and we plug into it polynomial P1. So let's see what this means. Well, it means that we take P of x, P1 of x, and we square it, or we multiply it, and we multiply it by P of x minus 1, right? So we can call this this is P1. We can call this new polynomial, let's call it, I don't know. Well, we actually called it C of P1, right? So I'm not going to call it anything. But what I want to point out is that the degree of C of P1 is actually at most 2 times 10 to the 7. So the degree went up because we had a multiplication here, but the degree went up in a controllable kind of way. And that's what we call the multiplication property. It is the property that when you multiply 2 degree D polynomials, what happens to their degree is pretty well understood. The degrees add up. So if you're squaring a polynomial, its degree at most doubles. And the main thing is that we have pretty good control over the way the degree grows. Now, why is this interesting? So that's so here's another sort of claim. P1 of x evaluates to a Boolean value on S if and only if this new polynomial C of P1 of x actually vanishes on S. So let's just look at this. So clearly, if it is the case that P1 of x evaluates to either 0 or 1 for every point on S, clearly it implies that when you plug C1 of x into C, when you plug P1 of x into C, you will get something that vanishes on all of S, because C vanishes whenever it gets something that is 0, 1, and we assume that P1 gives you 0, 1 on S. And it's not too hard to show the other way around, because if it vanishes, it means that P1 of x takes the value of 0 or 1 on S, and that's what we want. But now we have this fact that we used earlier about batch 0 testing. And this fact says this happens if and only if there exists some other polynomial that we called P tilde of x, such that two things hold. The first one is that P tilde of x times, well, sorry, let me erase here. P of x, C of P1 of x equals P tilde of x times Vs of x, because that's what the fact gave us. And the second thing is that we have control over the degree. So the degree of P tilde is going to be actually less than, well, 20 million. So it's like 2 times 10 to the 7, which is the degree of this guy, minus the size of S, well, which was 1 million, if I remember correctly. So let's go back to the challenge that we had. Now with this claim in hand, we can go back to the challenge and see how we can solve it succinctly and with very high probability. So this is the challenge that we wanted solved, right? We want to know whether P1 of x. So what we're going to ask for is, we are going to ask for, D1 is going to equal 10 to the 7. D2 should equal basically 2 times 10 to the 7 minus 10 to the 6. That's what we send. And now we get P1 and P2. We sample a single Z. We get P1 and P2. And the way we decide is, so we decide yes, no, yes, if and only if the following thing holds. If and only if, when we take C, plug into it the value that we got for P1 of Z, if that thing equals P2 of Z times Vs of Z, then we accept. Otherwise, we reject. So let's see again what's happening here. Suppose, let's talk about completeness and soundness. Suppose the prover is honest and P1 indeed gives you a bit for all of the first million, for all of the million entries inside this set S. So everything works well and you answer yes. On the other hand, suppose that P1 of z does not equal 0 or 1 everywhere. Let's suppose that on some point here, on the point, 7, whatever, 777. On this point, it doesn't equal 0. It's a lucky number, right? So, and everywhere else, sorry, on this point, it actually equals, P of this thing equals 7. What else could it be? What happens? So what happens is that when we look at C of P1 of Z, it is not a polynomial that vanishes on all of S. And since it is not a polynomial that vanishes on all of S, you cannot write it in this way. There is no way to write this, the left-hand side, as the product of Vs of Vs times some other polynomial of low degree. There is no way. And it's not hard to see it because Vs vanishes on all points between 1 and 1,000,000. It also vanishes on the point 7,777. But the left-hand side is some polynomial that we know does not vanish when you plug into it the number 7,777. So the left-hand side cannot equal the right-hand side. But now we have two different polynomials, and their degree is at most 2 million. Well, sorry, 20 million. It's 2 times 10 to the 7. So the probability of having an error because of that is at most 2 times 10 to the 7 divided by whatever is the domain from which we sampled Z. And again, we might as well take, P to equal whatever, 2 to the 256. Some huge number. So this will be a very, very low probability of error. So let's see. Sorry about that. Going back to the properties that we want. Going back to the properties that we wanted. So polynomials have the multiplication property. And this multiplication property gives us the, because they have the multiplication property, this implies that we can encode constraints. I have to write really slowly for this to actually register. We can write constraints about any computation. So it's a leap of faith to go from the simple constraint that we just described that just checks if an array is of Boolean type to a generic computation such as checking whether 10,000 transactions have been correctly signed and executed. But so the way to go from what we saw to general computation is to understand that one can break a general computation into a larger number of constraints. So it's not just about Booleanity checking. There's a whole bunch of other things that we could use. But I want to sort of summarize and go back to sort of the main theme that we started with. So let me just sort of go back here. We started with a question that asked, what is it about polynomials that make them useful when we want to prove statements of computational integrity that seem to have nothing about, nothing involving polynomials at all? And we said that there's this, general purpose proof system that is too good to be true, in which if the verifier specifies a bunch of degrees and the prover gives access to a bunch of polynomials, then a single sample actually suffices to prove any statement that we care about. And then we went a little bit deeper into understanding what is it about polynomials that lets you do this. So we mentioned 3 properties. These are not the only ones, but it's enough for one time. The first one is that polynomials are excellent error correcting codes, and they allow a whole lot of redundancy And this is what allows you to do good sampling, which is the analog of polling, which is what you do when you want to estimate with high probability the outcome of some computation, like an election. And because we have good polling or sampling, this allows us to do things very succinctly. We don't have to go over all of the computation and replay it or check all of its properties. We can just take a single sample that will sort of attest with high probability to the correctness of a very large set of statements. That's the first property. The second one is that the way we can effectively do this batch sampling or check a whole bunch of constraints at the same time is by this beautiful property of polynomials, that they sort of factor nicely into something. So if they vanish on a set of points, and even if this set of points is pretty large, there will be some structure to them, and the structure means that you can sort of write them as the product of two other polynomials, one of which you actually know exactly what it is. It's the vanishing polynomial on the set that you care about. So because you can sort of pre-compute this vanishing polynomial, and it is fixed and depends only on the set of points that you want to check your property, you can have this set be as large as possible, as large as you want, and still do it with just a single sample. And the third one, so far this only allows us to sort of sample and check basically just that a polynomial is zero at a large number of points. But the third property allows you to sort of reduce or take any kind of computation or any set of constraints that you care about and convert it into basically the property that you can solve in number two. You can basically reduce it into a special case of checking that a polynomial vanishes on a large number of points, which you can do by sampling. So these are just three of the properties of polynomials. There are many, many others, all kinds of symmetries of them, and the fact that you can, for certain vanishing polynomials, they have a very succinct representation, meaning that the number of coefficients that are non-zero is very small. I don't have time to go into that, but these are very important aspects. You can also encode and decode extremely fast with polynomials, which is another thing that is very important. So these are not all the properties that are special about polynomials, but it gives you some sort of informal intuition about why polynomials are so useful when you want to construct general proofs of computational integrity for general statements out there. So I'm gonna go back to answering questions, and I want to already while you're asking your questions and putting them or voting on them, I want to do a poll on what might be the next informal topic. And one of the things we can talk about is sort of soundness, or the sound of soundness. So soundness is this mysterious, or soundness analysis is this really deep aspect of understanding proof systems. It's the part that looks at what happens when a prover tries to cheat. How can we show that the prover doesn't actually get away with cheating? Because usually the completeness part, seeing that an honest prover can do things correctly, is the easier part, and it's the harder part to show that something actually can be rejected if it's false. So that's one possible thing. Another topic that is lighter from a mathematics point of view would be sort of how can information, or how can a proof be knowledge? What does it mean to have a zero knowledge proof? A little bit more from a sort of formal mathematical point of view. When we say that something is zero knowledge, what do we mean by that? How can something be zero knowledge? So a little bit about the informal intuition about zero knowledge, along with a little bit of math and how one might achieve a proof that is zero knowledge. And then the third topic that we could talk about could be sort of going back to story time, maybe inviting some folks from the earlier days of proof systems to sort of ask about the evolution of proof systems, of models of proof systems, to see how it looked back then, what was the intuition back then, what surprised them, what was interesting. So we'll write this poll in a second, and you're welcome to answer it, while I'm going to sort of answer a few questions. How do you map the computational statement to the polynomial? That's a very good statement. That's a very good question. So, I mean, I gave you one example, which is the sort of type checking, right? Suppose all you cared about was just doing a type checking, right? That's all of the computation. You just want to know that this array that is represented by a polynomial of huge degree happens to have Boolean type on the first million entries. So you saw the specific way we do it. We define a domain on which we care about. That was the domain S, and we constructed the vanishing polynomial for S. And simultaneously, we constructed also a constraint polynomial, which was C. That C was a quadratic polynomial, a very simple one. So if you have a more elaborate computation, you're going to need maybe more constraints. For instance, maybe you want to know that the set of values was not Boolean, but computed, let's say, the Fibonacci sequence. So now your constraint is not going to be, just looking at a single entry and raising it to squaring it and doing that thing. Your constraint is actually going to ask for the value of the polynomial at more than one point. It's going to ask for the value of the polynomial at time, I, at I minus 1 and I minus 2, and sort of take the first two entries, sum them up, and subtract them from the third and see whether that is the case. There are, of course, much more elaborate constructions. For instance, maybe you have a few registers that you want to track over time. Maybe one of them was this polynomial P1 that you want it to be a bit, but then based on the value of that bit, there's this other polynomial P2 that you want to sort of alternate between two possible things. Maybe if the bit is 0, you want to, add two numbers. If the bit is 1, you want to multiply two numbers. So for that, you're going to have more constraints and more polynomials. There'll be one polynomial, which is P1, and then there'll be another polynomial for tracking, the program. And I see here that Dimitris is suggesting that maybe the question of mapping a program to a polynomial could be the topic of the next one. I could, we could certainly work with that. That would be pretty good. I just want to point out that for those of you who want to actually, get their hands dirty with actual codes and also even write constraints for systems, so Starkware did a very nice Stark 101 workshop. All of it is available online, including online lectures and examples, and it is for some very simple program. But definitely it doesn't contradict. I see there's a lot of support for this, so we can sort of we'll see what the poll comes out to, but we can also add that to the poll. And I wonder if I can edit it somehow online. So I see people like this. So I see there's suggest your topic in the chat. So for suggest your topic in the chat, let it be what was suggested there. The question of mapping. I want to try and edit this. So okay. It actually appears here. Mapping a program to a polynomial. So you're also welcome to vote for that if you want. That's also an excellent topic. Okay, I'll go back to answering more questions. Just one second. So the next question, can you say anything about the probability theoretic proof of zero knowledge and or soundness? Well, I can say a lot about the proof. Actually, in the model that we were describing, the proofs are very, very clean and simple. But I think this deserves a, this is basically asking, can you compress the two offered talks, right? One was on the sound of soundness and the other was on what do we mean by zero knowledge into one short answer. So I prefer not to do it and give it its proper time. But there are very clean and nice proofs for both soundness and for, how do you get zero knowledge in the model that we talked about. And in particular, actually, the soundness is, soundness error is the probability of error that I was discussing earlier. So actually, we sketched abound on the soundness error for those simple protocols, for the batch zero testing and for the Booleanity checking. So it was literally the degree of the polynomial divided by the domain from which you sample. So it was D divided by P. And that was the proof. The proof is basically that if the two sides of the polynomial equation are not the same, then they can agree on at most the degree of the polynomial many points. And because you're sampling from a much larger domain of size P, the probability of error is only at most the degree divided by P. That's about soundness for this case. But when I meant soundness analysis as a topic, I wanted to go a little bit deeper into how one actually discusses soundness for more general statements, like, checking proximity to low-degree polynomials, checking proximity to general properties, and so on. And zero knowledge deserves its own talk. Okay, next question. Are computations with branches or iteration more difficult to map to a polynomial? Not really. Not really. So, no. I mean, we assuming we'll have a special session on that, we'll actually go into details about how do you deal with iterations and with branches. But in a nutshell, you ask the prover to basically tell you, whenever there's a choice to be made, you ask the prover to tell you what choice has been made and prove to you that that thing has occurred. And you can do similar things with iterations. There are various tricks you could do, but like one of them would be to sort of require the prover to do the counting and terminate at the right time and prove that it terminated at the right time. There are other tricks you can do as well, but it's not inherently more complicated. You need more constraints, sometimes the degree of the constraints is slightly larger, but it's not. Okay. Next question. The degree of P is less than D. How tight should the estimation be if we don't want to reveal the degree of P? Can we use the upper bound? Yes, certainly. So often, let's say in the context of a zero knowledge proof, you actually don't want to have the prover reveal to you the degree of P. But it's perfectly fine to just have the prover prove to you that the degree of polynomial is less than D. And even if the degree is 0, for instance, everything works well. So you don't have to reveal the exact degree of D. It's enough for the verifier to know an upper bound on the degree of D. Good question. Okay, what should I search to read more about point 2, efficient zero testing? So I will send, first of all, a link to, just like I did last time, I have another videotaped presentation I gave 2.5 years ago. And I have, I think, another one more recently that goes a little bit more formally into the mathematics of this particular point of zero testing, and also how you can make it more efficient. I'll just say in a nutshell that you can sort of the way you can show the basic property is you start with a statement that a polynomial vanishes at 0 if and only if x divides the polynomial. You can write it as x times some other polynomial. And from that, you can generalize to get the whole efficient zero testing. But I will send in an email some information in video links and maybe a presentation that folks can follow and learn more about that. Okay, next question. It looks like we can achieve the same properties with multivariate linear combinations. Terrific question. Do you think we can substitute the equations of polynomials of degree 10 to the 6 with many linear equations? That's an excellent question. So actually, if you use multivariate polynomials, you get some really amazing and better properties. For instance, sort of with a polynomial that is in a single variable, so the degree equals the number of symbols that you want to discuss. With a bivariate polynomial, actually the degree becomes square root of the amount of information. With the degree 3 polynomial, it becomes cube root, and this goes on. And if you use a multilinear polynomial, as you suggest, then you can actually have the degree be 1. This comes with a hefty price, because multivariate polynomials, if you want to sort of deal with them or evaluate them, you need to evaluate them not over a field or over a domain, but over the direct product of a field with itself. For a bivariate and for a trivariate, you need to work with the field cubed and so on and so forth. And this leads to a lot of inefficiencies, but in terms of soundness and abstract properties, you get amazingly good proof systems with those systems as well. Moreover, if you go into the literature, the early literature up to the early aughts, from like mid 80s to the early aughts, all of the discussion of proof systems involved only multivariate polynomials. So there were no proof systems built with univariate polynomials, and in fact, you needed the sort of degree reduction property in order to construct proof systems back in the day. So definitely multivariate polynomials are very, very important and well studied. They don't show up that much in, I mean, they make an appearance in practical proof systems, and they certainly underlie a lot of the analysis, but that's a more advanced topic. Okay, so let me go back to the poll, and let's see. So it seems that there's interest in mapping a program to a polynomial. Okay, so we can make that the topic of the next one. I want to try and keep this pace of, let's say, once a week for this informal thing. I just want to say that next week, at least for me, I'm going to have to make it later, because here in Israel, it's Passover, and I'm going to need to sort of make it a little bit later, or either find another date, but we'll sort it out online. And you can see in the chat room the Stark 101 online course. Thanks, Avi. And you can sort of see some examples there for mapping a program to a polynomial. So I just want to end by saying, if you have other direct questions, you're definitely free to write to me directly at elliot@starkroad.co. And thank you so much, and see you next time. So I'll stay around a little bit for the chat room and this and that, but I think I'll stop the broadcast and then hang around. Thanks a lot, all.